In this presentation, we will briefly talk about other important sensor technologies for urban climate. One is Lidar data, and the other is drone-based photogrammetry. The left figure shows point clouds gathered by Lidar, or light detection and ranging. Ranging means the estimation of distance. The top figure shows an impression of data footprints. The bottom figure shows the final large-scale 3D product derived from the Lidar point cloud. To the right, it shows large amount of overlapping images gathered by a drone. With different vantage points, drone-based photogrammetry is now a standard technique for 3D reconstruction. 3D reconstruction and digital twin in GIS can be used for urban climate models. Lidar stands for Light Detection and Ranging. It is an active sensor. The method uses near-infrared pulsed laser to get the shape of objects. A Lidar instrument principally consists of a laser, a scanner, and a specialized GPS receiver, and can be mounted on airborne platforms, including drones. Bathymetric application is also possible with penetrating green light to measure sea floors and riverbed elevations. How is Lidar data collected? The instrument is pointed at a target. The pulsed laser beam is emitted towards the target. Then the reflected laser beam is recorded by the sensor. The traveled time between the sensor and the object will be used to measure the range or distance. This laser range is then combined with position and orientation data from GPS, IMU systems, and scanned angles. The result is a dense, detail-rich point cloud. Each point in the point clouds carries 3D spatial coordinates, latitude, longitude, and height. The point clouds are used to create digital elevation models, canopy models, building models, and contours. This is an example of an airborne scanner from the National Oceanic and Atmospheric Administration of the U.S. government. The study site is a coastal area with a lighthouse in Florida. The products are used to activities such as inundation and storm surge modeling, hydrodynamic modeling, shoreline mapping, emergency response, hydrographic surveying, and coastal vulnerability analysis. This slide shows an AI product of 3D models of all the buildings in a city. It will be very useful for climate adapt planning. Lidar mapping services can improve the way cities are designed, managed, and developed. The highly accurate elevation data allow urban planners to create precise and detailed terrain and topographic maps. This information is invaluable for identifying potential flood zones and designing appropriate drainage systems. With Lidar, planners can assess the suitability of different areas for development and make informed decisions about land use. For urban applications of Lidar, we can find similar lists from service providers. The products are typically used for city mapping, urban planning, vegetation mapping, power lines monitoring, coastal mapping, and archaeological and historical surveys. This slide already appeared in the last presentation. It shows the 3D representation of trees. This information is important for ecological studies and species identification. The product is used to investigate urban green. For urban climate modeler, Lidar point clouds are used to predict thermal comfort in the city. The 3D Lidar product with meteorological data can simulate tree shadows during hot summer day with different sun angles. This has been discussed, and you should have practiced the model in the urban multiscale environmental predictor exercises. Lidar data can generate very accurate product, but it is an expensive operation. With the increasing popularity of drone-based acquisition and related technologies, 3D reconstruction can also be achieved using drone-based photogrammetry. Photogrammetry and professional high-resolution cameras can generate 2D and 3D surveys. With their absolute accuracies down to 1 cm root mean square errors for horizontal and 3 cm root mean square errors for the vertical. The cost is considerably cheaper. What is photogrammetry? A drone captures a large number of high-resolution photos over an area. These images overlap such that the same point on the ground is visible in multiple photos and from different vantage points. Photogrammetry uses these multiple vantage points in image to generate a 3D map. The 3D point clouds include also texture, shape, and color for every point on the map. Drone-based photogrammetry is cost-effective and provides more flexibility in acquisition comparing with Lidar. Photogrammetry uses the same principle that human eyes or 3D videos use to establish a depth perception. It allows the user to view and measure objects in 3 dimensions. About their limitations, it is a passive technology. Therefore, it needs light source and illumination to detect objects. In comparison, LiDAR sensor with laser pulse can detect objects without light. Here is an online webpage comparing the two methods, LiDAR versus drone-based photogrammetry for 3D reconstruction and other applications. The image on the top shows the ortho mosaic of the study site and the digital surface model generated by the method. The bottom left image illustrates the acquisition plan and different vantage points. The bottom right image is the LiDAR point clouds of the study site. This example shows the product of the city Bordeaux. It is a showcase project called Leica Real City. The visualization is done by the company Leica Geosystems. The product represents the fusion of oblique and linear imagery, point cloud, and terrain data. This is an impression of 3D reconstruction using drone-based photogrammetry. Pay attention to the very high level of details. There are many online videos with tutorials on LiDAR and drone photogrammetry. Here are some of more popular ones for your reference. They provide a quick review of the technology. Please check them out. Here is a list of the websites and references used for this presentation.